am recording. Okay, and I'll begin by sharing my screen with you so you can see where we are. I'm going to share my browser. And we're currently in week 5 of our course. Okay, we already completed derivatives of formulas part A, which introduced things like using the power rule to take derivatives of polynomials or power type terms in your function. We use the constant multiple rule, which lets us just pull constants that are coefficients that are multiplying a term through the derivative process. And we also reviewed a few rules of exponents, which turn out to be super important in simplifying function expressions before you actually try to do calculus on them. Okay, so if you go on down here, okay, I'm trying to see, I didn't put it in here, but I'll go to our notes, our online tools module. This is near the bottom of the course. And again, I'm sorry if it sounds like a broken record, but I've got different folks joining on different days. I want to make sure everybody sees it. Okay, so here's the final exam. Here's the textbook, Online Tools for Math. Okay, I want you to realize that in this Online Tools for Math, you can see, you know, all the tools that you can use when you're taking an exam, when you're doing your homework. And yes, I want you to use the tools. Okay, it's not cheating. Okay, it's the way the real world works, is you use tools to do your job. Okay, so we've got Desmos, a scientific calculator. This is primarily for folks who don't have a TI handy. Here's properties of exponents and logarithms. Okay, so in case that stuff we talked about last week was a little hazy, in other words, why 1 over x can be written as x to the minus 1, fractional exponents, all that stuff. Here's kind of a short summary, and again, it's got some examples with it, with each of the rules. Okay, here's a couple of applets, slope of a secant line. This applet plots the derivative in a function together, so you can see what they look like. All right, this is, again, this applet can be handy if, for example, a question saying, hey, suppose I have this function, here's a graph, what does the derivative look like? That's what this applet does. Okay, here's a factoring calculator. If it's a little hazy on how to factor a polynomial, remember factoring quadratics? That was a while ago. So this applet calculator will actually help you with that. Okay, so again, here's a sheet that's got derivative rules with examples. This may not make a whole lot of sense till we get through most of the stuff in Unit 2, but it's here. Okay, so all of this stuff, like down to derivative rule summary, is stuff you can use. Again, it's all in this one module, so you can find it easily. Okay, going back up to week 5. Okay, I just want to show you, I'm going to be using derivative rules part B notes. Okay, so it's in week 5, and again, it's part B notes. Okay, I'm going to open up the chat in case anybody's got questions, but I'll begin by sharing those notes with you. And again, this takes me a minute, sorry. All right, let me share the notes now. All right, so everybody should be able to see derivative rules part B on my screen. Okay. And again, if you've got questions going along, type them in the chat, but it's just as easy to unmute yourself and just ask. Okay, no problem with stopping the train if it's not making sense. Okay, I want to begin by reviewing a topic from college algebra, which you might remember is function composition. part of what you need to do when you're doing calculus is to figure out how to actually set it up, okay? And part of that requires that you be able to recognize what it is, what the function is that you're looking at that you want to take the derivative of. We kind of touched on this briefly last time when I introduced the product rule for a derivative and the quotient rule. In order to use those, you've got to recognize, hey, do I have a product or do I have a quotient? Okay. The rule we're going to introduce today, which is called the chain rule for taking a derivative, is used on compositions of functions. Okay, and I found from teaching calculus for a while that some students get confused between when is it a product and when is it a composition. Okay, so that's what we're going to review. Okay, so I'm saying be able to tell the difference between a product of two functions and a composition. In a product, the two functions are next to each other because they're multiplied together. So in this example here, my function y is a product of 5e to the x and x squared. You can think of this as the first function, f, and this is the second function, g. Okay, so the two functions are right next to each other. They'll usually be separated by parentheses in some way, okay, but not always, depending on the functions, okay? And again, what you want to do is you want to be able to recognize, okay, my first function is exponential. My second function is polynomial, right? Because remember, you kind of need to know the type of function in order to be able to know what derivative pattern to use to take the derivative, okay? Exponentials have their own pattern, okay, which is really easy for e to the x. This derivative is the same as the function. Polynomials, you've got to use the power rule. Bring down the exponent in front and then drop the exponent by 1. Okay, so it's important to not only recognize, hey, I've got a product, but also what types of functions are being multiplied together. Okay? Compositions, on the other hand, have one function inside of the other, okay? You might remember the terminology inner function, outer function, okay? So basically, the first function that gets the x value, the input function, the input value is the inner function, okay? So take a look at this function, y. It looks really similar to this. The only difference now is x squared is inside of the exponential function. So you can think of this as g of f of x. Actually, let me do it the same way so the g's and the f's are the same. F of g of x. Okay, where the g of x is the x squared in the exponent, and f of x is my outer function, the exponential. Okay, does everybody see that? Does everybody see that I've got a polynomial inside my exponential? It's acting as the exponent. Okay, so this is a polynomial inside an exponential. Okay, and it turns out if you're doing calculus by hand, you need to distinguish between these two situations. Because in this situation, you're going to use the product rule, and in this situation, you're going to use another rule that we're going to introduce today, okay, the chain rule. Okay, so it's important to look at your functions first, okay, and be able to tell what you're looking at. Okay, so let me ask questions so far. Anybody have any questions on this distinction? No questions? Okay. All right, so what I'm going to ask you to do is I'm going to put up a couple of functions on the screen, and I'm going to ask you to tell me if they're compositions or products, okay? We'll do a couple at a time. I've got like 5 of them. Okay, so let's do just A and B for now, okay? So look at A and B, okay, and type composition or product. And then we just put them in the chat, okay, with the letter. Okay, so that's what I'm asking you. Look at A and B, type composition or product. So say A, and then tell me what you think it is, and on the same line, B and what you think it is. So we're just going to look at these 2 to start with. Okay, the first 2. Right? Okay. So you've got to tell me what it is, all right, composition or product. All right, so you've got a choice. In other words, the letter by itself doesn't really tell me anything. Just tell me whether you think, is this function A a product of 2 functions or a composition? Let's do A first. Product or composition? Okay, let's do them one at a time. It's too confusing otherwise. Okay, unless you're going to talk to me. If you're going to type in the chat, it's too confusing to do 2 at a time. All right, so let's just do A. All right, and you tell me whether you think A is a product or composition. Okay, I'm getting some votes. Everybody put something in the chat. What you think? Okay. All right, so I've got a couple of people who've got something in there. I think only 3 of you, but there are more than that on mine. Okay, product. Good. Okay, so yes, this is a product of a log and an exponential. Okay, so you can think of this as f of x times g of x. Okay. Now let's try B. How about B? What do you think? Okay, and would you want to think, if you think it's a composition, try to think about what it's a composition of. Okay? What's the inside function? What's the outside function? Okay, take a minute. Okay, I'm getting a bunch of compositions. Anybody else? Good. Okay. This might be easier to just unmute yourself and speak it because it's too many words to type. What function do you think's inside and what function's outside? Okay, somebody want to unmute yourself and just explain? What are you seeing? Oops. Anybody? If you want to type it in the chat, you can do that too, but it's a lot easier to just talk. Okay. I'm asking you a question in the chat. What's the inside function? What's the first one that gets x? the inside function. That's how you tell it's the first function that gets x. Anybody?
Exponential? Is it
Okay, well, do you think these are exponential functions or are they some other kind? Okay. All right, me is saying the quadratic function. Okay, you've got a polynomial inside a polynomial here. Okay, so I'm going to say degree 2. Inside a polynomial, degree 5. Okay, so the inner function, the first function to get x, in other words, if I start putting values inside of g, the first function that's going to get those values is this quadratic in here, right? You're going to do whatever the quadratic says to do to x, and then the next thing that happens is that value is raised to the 5th power. Okay? If you remember how compositions work, your inner function gets x first, does some stuff, and then passes along that output value to the outer function. Okay? And then that does some stuff, and it produces an output to the whole composition. Okay? You might remember pictures, and again, I apologize because I don't know what you've seen before. Okay, so you can think of it like this, where you've got an input function, say g of x, okay, and then it does some stuff. It gives its output to f of x, which then has the output here. Okay, so you throw an x in like that. Okay, f of g of x. So that's a picture that shows you what's happening with the composition g. The inner function gets it first. Okay, it gives the output of g to the outer function, which then gives you your final output. Okay, I know this is hard to wrap your mind around concept in college algebra. And again, the only reason I'm going over it here is not to reteach composite functions, but so you can recognize not only that you have a composition, here's the 2 things you need to be able to do. Recognize it as a composition, decide which one's inner, which one's outer. Okay, that's all you have to do in order to be able to do calculus on these things. Okay, it's very important if you're looking at something you're going to do calculus on by hand, and by that I mean without a computer, okay, is to figure out what the shape of it is so you know how to approach it. In other words, which pattern to use, which tools to use, okay? Calculus isn't an undifferentiated mass of stuff, okay? It's this tool for this situation and that tool for that situation. So that's what we're trying to figure out here. That's why I'm taking the time to do this. Okay? So it's a degree 2 polynomial inside of a degree 5 polynomial. So it is a composition. Okay, take a look at C. Okay, what about C? What do you think? Okay. I'm asking composition, product. What do you think about C? H of x. Okay. Anybody else? Remember, if you're telling it's a composition, you need to be able to tell me inner, outer. What's on the inside, what's on the outside. Okay. Anybody else? Okay, got a couple. Good. You're all getting the composition versus product right, which is excellent. Most calculus classes don't do as well as you are. Okay, so it's a composition. of, okay, what's the inner function? The first one to get x. Okay. Anybody agree or disagree with what me is putting in? Okay, yes, the polynomial is inner. Okay, so polynomial inside a log. Good, good, good. Okay, polynomial is the inner one. Okay, let's move on. How about D? Try D. Okay, what do you think? Again, is it a product or a composition? Okay, and again, if you're thinking composition, the next thing you should think of is, all right, which one's inner, which one's outer? Okay, and if it's a product, can you identify the two functions multiplied together? Okay. All right, so again, if you're saying it's a product, you should be able to identify one function of x multiplied by a second function of x. Okay? If it's a composition, you need to find one function of x inside another. Okay, so let me see how we're doing on this one. I have one composition and two products. Anybody else want to vote? That's not everybody. Okay, I got another composition. So you're tied. Two products and two compositions. Okay. Another product, a tiebreaker. Okay. All right, some products. Okay, let me ask the people who are saying it's a product. If it's a product, what are the two functions multiplied together? And then think about what family do they belong to? What are the two functions multiplied together if it's a product? Feel free to unmute yourself and just talk. It's okay.
Wouldn't it be like natural log and exponential?
Okay. Is there an ln in because you're saying natural log? Okay. Anybody else want to give it a shot? I do see the exponential for sure, but I'm not sure where. I would think if I were going to see natural log function, I'd see an ln somewhere, and I'm not seeing that. Somebody else want to try to explain? A bunch of you said product. I want to know what you're thinking. It's important to me. I want to know how you're seeing it. That helps me explain it better. Somebody else want to give it a try? Nobody? I think we had more products than compositions. Okay. I guess I'm seeing, I'm guessing you're seeing this much of it as an exponential function, right? E to the minus 0.03x, that's an exponential. What's going on in the exponent? Oh boy, what's happening up here in the exponent? There's some number multiplying x, right? Okay. And what's this 4.2 out there? What's the 4.2 out in front? Is that a separate function? Okay, Ryan's saying no, it's a leading coefficient. So it's part of the exponential? Is it part of the exponential? What do you think? Should I do this? What do you think? Okay. If it's a leading coefficient, then is it a separate function? This would be so much more fun if you guys would unmute and talk. It's like having a discussion on paper. It's kind of strange. Okay? It's more important for you to think this through than it is for me to just tell you what it is. Okay? Because if you're the one talking, you're the one thinking about it. Okay? It's real easy, particularly in a virtual math class, to be extremely, just let the whole thing just roll on by and listen to it. But you actually learn more if you participate. Okay, so I've got somebody saying that it's not part of the exponential, and I'm asking if it's a separate function, and somebody else said no, which would lead me to believe then it is part of the exponential. Okay?
Would that 4.2 only be separate if it was in parentheses?
Okay. 4.2 is a constant, right? And in this case, it's multiplying this exponential. You're absolutely right. It's multiplying the exponential. But my question to you is there an x associated with 4.2? And the answer is no. So you can treat 4.2 as a coefficient on the exponential. It's not a separate function, right? And this is something that folks do all the time. They start looking at coefficients just because they're multiplying something. They assume, they overgeneralize and say, well, it must be a product of two functions. But it's not, okay? There's no x here. If I had this, oops, hold on. That's a product, right, of a linear and an exponential. Okay, that's a product because I've got 4.2x e to the x. If it's just a constant multiplying your exponential, it's a coefficient on the exponential. Okay, so I guess I've kind of spoiled it here saying this is not a product. So that must mean this is a composition. But what is it a composition of? What's the first thing that gets x? So in other words, if I put an x into j of x, what's the first thing, what's the first expression that gets x? It's up here in the exponent, right? Okay, and what is that? That's like a linear function. Y equals negative 0.03x. Okay, so you can think of it as a linear inside an exponential. Okay, so this is g of x, right? linear, and then the whole thing is f of x. So the first thing that happens is you feed x into that inner linear function. It's going to multiply your x value by negative 0.03 and then pass it on to the exponential as an exponent. Does that make sense? And then the final step, your exponential is going to multiply by that 4.2 that's hanging out there as a coefficient. Okay? Does everybody understand what all the pieces are? Okay? Part of what I try to do in calc is to try to tie up the loose ends from college algebra, because I know there's lots of them. Okay, you cover a lot of material in college algebra. Not all of it is clear when you're done. Okay, so please ask, does everybody understand this problem? Okay, that it's a linear inside of an exponential.
Yes.
Okay, now some of you might be thinking, I can hear you thinking, okay, but isn't plain old x a linear? Yes. But the reason I don't need the chain rule for that is because the derivative of x is just a 1, okay? And that's not going to affect anything. The derivative of negative 0.03x ain't 1 anymore, okay? It's 1 times negative 0.03. So this thing is going to have to tag along somehow, okay? So that's why it's important to look at this like a composition. Okay, last one. Okay, try E. Okay, is E a product? I'll make this one even an easier one. So product, quotient, or composition. Product, quotient, or composition. Think about it before you answer. What do you think? Product, quotient, or composition? You might want to mentally use some algebra to rewrite it if you can. Okay, but think about it for a minute and then vote on one of them. What do you think? All right, everybody is kind of getting wise to me, huh? Okay, I'm glad none of you are saying it's a quotient. Some of you are thinking about, wait, it looks like a fraction, doesn't it? Okay, the thing is, I can rewrite this way because there's no x's in the numerator. This can be rewritten like this. Right? So you can think of it as not necessarily a quotient. I mean, technically you can use the quotient rule on it, but it's going to be pointless because the derivative of your numerator is 0. Okay, so it's like a lot of fuss for nothing. Okay, what's more sensible is rewriting it like this. So I would say this is a composition of a quadratic inside a rational. Right? Because it's 1 over something squared. Okay, so that's like a rational function on the outside and a quadratic function on the inside. So here's g of x. And then the whole rational thing. Okay, where u is x squared minus 4. Okay, so that's your outer function. Anybody big questions about the 5 examples? Questions on the 5 examples. So we've spent like 40 minutes and we haven't done any calculus yet. That's important. Okay, I wouldn't have spent the 40 minutes otherwise. If you understand what you're looking at, applying the patterns makes a whole lot more sense. If it's not clear what you're looking at, you can stare at the patterns forever and not know what to do with them. And that's super frustrating. And I'm trying to avoid the frustration. Okay? So not seeing questions. So let's move along. Okay, again, this is from your text. But again, please be forewarned. I am not showing you all the examples in your text or all the information in your text. So it's still worthwhile to go through that, like read it, okay, and look at the videos. Right? Some of the notation for using chain rule is confusing to people, okay? I want to try to make that as clear as I possibly can. Okay? So again, they give it to you in two different notations, right? And I want to try to explain the notation. So basically, we're talking about composition of functions. All right, that's when you need the chain rule. And this notation up here says, we've got a composition called y where the outer function is f and the inner function is g. Okay, and the way they're showing that here, they're saying y is f of u where u is g of x. Okay, so this is like saying y equals f of g of x. Okay, everybody kind of get that? They're introducing this other variable u to make it clear that u is your inner function. Okay, so u is the inner function g of x. Okay, everybody good with that? Okay, you will also see the chain rule, okay, in what they call Leibniz or differential notation. That's another term for these fractional things. This says the derivative of y with respect to x, because x is your input variable, right? So you want to see how y is changing as x changes. That's what the with respect to means, okay? Is the derivative of y with respect to u. Okay, so what that's saying is take the derivative of the shape of the outer function, and then differentiate the inner function with respect to x and multiply them together. See the multiply here? Whoops. Sorry. My bad. Here we are. Okay. There's a multiply here. Okay, the du's seem to cancel, okay, and you get dy dx, okay, but all this is showing you is how the chain rule chains together, okay? So basically, derivative of outer function times derivative of an inner function, and they say that down here in words. The derivative of a composition is the derivative of the outside function with the inside staying the same times the derivative of what's inside. Okay? So if you're thinking chain rule, think derivative of outer times derivative of inner. Okay? And I'll show you how it works. We'll do plenty of examples. Okay? Here it is with prime notation. I find this worse than useless. Okay? Don't bother. Okay? Too hard to understand. Okay? So let's take a look at some examples and we'll actually play with it, okay? So I have a function f of x, okay? It looks like a polynomial inside of another polynomial, right? It's not a product, it's a composition. Okay, so my outer looks like something to the fifth, okay? And my inner is x squared minus x minus 6. Okay, I've deliberately left the parentheses alone. Okay, I haven't put anything in here. Okay, sometimes when I describe it, I think of this as this is your inner function, but we're going to leave it alone. Right? In this notation up here, you would have u. Okay, u to the fifth. Okay, so if I want to use the chain rule, first thing I do is I differentiate my outer function. Well, my outer function is something to the fifth, so I can use the power rule on that. I'm going to bring down the 5. Here's my parentheses and drop the exponent by 1. Okay? And remember, in words it said leave what was in the parentheses alone. Okay, that was x squared minus x minus 6. Okay, that's just coming across for the right. Okay, so here's the outer function, right? I'm differentiating the something to the fifth. Now I'm going to multiply that by the derivative of the inner function, which is my quadratic. Okay, and I can use the power rule on that as well. Okay, if I differentiate x squared, I bring down the 2, drop the exponent by 1. If I differentiate negative x, I'm going to bring down the exponent and drop the exponent by 1. That means the exponent on x will turn into a 0, which makes it x to the 0. That's the constant 1. So the x disappears. Okay, you want to notice everything in the polynomial dropped by a degree. So x squared, that became a linear term, and the linear term became a constant term. Right? That's because this became x to the first, this became x to the 0. You need to know those rules of exponents for this to make sense. The 6, the negative 6 doesn't give me anything, okay, because when I differentiate a constant, it's not changing, so I get a 0. Okay, and here you are. This is done. Okay, it's the derivative of the shape of the outer function, leaving the inner function alone, okay, and then it's multiplied by the derivative of the inner. I'm going to stop and ask questions on example 1. Questions on example 1? Give me a yes or a no, please. Just give me a shout out so I know if I need
No.
to. We're good? Okay, no. All right. Okay, good. All right. Well, here's one for you to try. You try.
Someone
G.
had a question.
Sure, somebody. Why did I drop the 1 on 4? Okay, because I'm applying, what I'm trying to do here is I'm applying the power rule for differentiating. That says bring down the exponent in front and then drop the exponent by 1. It's the same rule I'm using over here when I'm differentiating the inner function. Bring down the 2 and then drop the exponent by 1. Okay, it's one of the patterns that we talked about last time for differentiating polynomials and power functions. Okay, is that better? Any other questions? Okay, good. And again, I know you're getting used to the rules, so you don't exactly have them on your fingertips yet. Don't feel, hesitant about asking. Ask. Okay? So I'm going to leave this up here for you to see it, and you try finding g prime of x. Okay, when multiplying 2, would we put it in parentheses? Yes, okay, technically, because you're multiplying the whole thing. Okay, so absolutely, yes. Okay, now a lot of time is spent in a lot of calculus classes simplifying things. Don't waste your time, okay? Unless the thing is really unwieldy and you need to use it for something else, it's okay to just leave it the way it comes out, okay? And more, our homework system should be fine with you not simplifying. Okay, so don't worry about that. Okay, so again, yes, this second term needs to be in parentheses because I'm multiplying both terms in here by this. So good catch. Thank you. All right, so you try finding g prime of x. Okay, that's right over here. Okay, do it the same way. Okay, type done when you finish. Okay, great, guys. I know some of you might still be thinking about it, and that's okay. But let's go through it together, make sure we're all in the same place. I deliberately tried to make this look like the last one so you could see how to scaffold it. My outer function is exactly the same. It's something to the fifth. The only thing that's changed here is my inner function. Okay? So again, the way you do the chain rule, you recognize it as a composition. This is again a polynomial inside a polynomial. So first I'm going to differentiate the outer function. It's a power, right? It's like a polynomial. So I'm going to use the power rule, bring down the exponent, leave that part alone, and then drop the exponent by 1. That's the power rule. Okay, and again, I'm just going to leave what's in here alone. So here's outer. And then I need to do inner and multiply the two together. Okay? So again, I'm going to put that in parentheses because I want to multiply all the terms by all the terms. Okay, so if I'm differentiating x cubed, I'm going to bring down the 3 and then drop the exponent by 1. And then 8 is a constant, so it's not giving me any derivative, right? Because constants don't change. So there's your answer. Okay, so take a look at it if you actually got through the whole problem. And if not, please ask.
Why did you put the square root on the x? I mean, the two.
Okay, what I'm doing is I'm using the power rule. Okay, the way the power rule works for taking a derivative. Okay, here's the way the rule works. Say your function is this. It's some number raised to a power. Okay? The power rule says to take the derivative of that, you bring down the exponent in front, and then you subtract 1 from the exponent. That is literally what the rule says to do. So I'm using, wherever I see a power and I'm trying to differentiate, I'm doing that. See, here's the 5. It came down in front, just like my n. And then I'm subtracting 1 from my exponent here. So here's the outer derivative. And then when I take the derivative of x cubed, I'm doing the same exact thing. Bring the 3 down in front and subtract 1 from the original exponent. See the n minus 1? Well, 3 minus 1 is 2. Okay, so is that okay? Anybody, anything else? Okay, please ask more questions if whatever I'm telling you isn't doing it for you. Okay, it's important that it makes sense. Okay, all it is a pattern. Okay, remember we said last time, what we're trying to do here with all these patterns is not necessarily stuff your brain with junk, but we're trying to speed up the process of taking a derivative. If you remember in the last unit, we had to take the limit as h approaches 0 of f of x plus h minus f of x divided by, that's too long and drawn out. We get the same result with these patterns. Okay, so it's a way to speed up the process. Okay, and again, just to remind you, this function f prime here, which is 5 times x cubed plus 8 to the 4th times 3x squared, this function will generate the slopes of tangent lines, and I'm sorry, it's not f, it's g, generate the slopes of tangent lines to the function g as we move around it at various x values. So this will generate the rates of change of this starting function. That's why I want g prime. Okay? We haven't done any applied problems yet, so this may just seem kind of pointless. Why am I doing this? We will use g prime for finding rates of change of a function we care about. Okay, so all we're doing here is practicing this skill. Okay, the 8 isn't on the inside because the 8 is a constant. So constants give 0 as their derivative. Okay, constants give 0 as their derivative because a constant isn't changing. And when we're taking a derivative, we're finding a rate of change. Okay, so whenever you see constants with no x's, they don't give you anything in the derivative. Okay, so far so good. We ready to move on to other types of functions? Okay. All right, let's take a look at this. Okay, here in H, I have a linear inside an exponential. Okay, so I'm recognizing this is not a product. The 2 out in front is just a coefficient. Okay, so all I'm going to do with the 2 is pull it through. I'm not going to mess with it. Okay, the exponential part is 4 to the 3x. Okay, the 2 is just multiplying the output of that, so it's a coefficient. Okay, so that's just going to get pulled through, all right? And then what I'm going to do is I'm going to differentiate the outer part, okay, which is the 4 to the 3x, okay, and I'm not going to mess with the 3x, okay? So if you remember how exponentials work, let me put it up here. If I have y equals a to the x, right, then I have y prime equals ln of the base times the same exponential. Okay, remember that from last time? Again, don't expect you to have it memorized. I don't expect you to memorize any of this stuff. The only advantage to memorizing anything is it makes the process faster. But I've given you a cheat sheet, and you have all these notes, okay, with all the formulas. Use them, okay, when you're doing your homework so you get familiar with the formulas, okay? And yes, you can use them on exams too, okay? Want to free up your brain to be able to actually apply calculus to real-world situations, okay? So leverage the memory work, okay? Use your notes for that, not a problem. Okay, so there's my pattern for an exponential function that has a base a, okay? So here's the way I'm going to differentiate h. move this down a bit. Okay, so h prime of x. First thing I'm going to do is pull through that coefficient. Okay, so pull it through. Okay, pull the coefficient through. Then I want to differentiate the outer function, which is my exponential. Okay, so that's 4 to the 3x. Okay, so that's ln of the base. And then repeat the exponential. Okay, everybody good with it? I'm using the pattern up here. Again, I got too many things on the screen, but hopefully you can see that pattern from last time. And then I have to differentiate my inner function, which is the linear. So if I want to differentiate 3x to the first, right, the 3 is a coefficient, just pull it through. The x to the first, bring down the 1, okay, which is going to multiply this. And then I have x to the 1 minus 1. Okay, so there's the differentiation of the outer and the inner. And this can be simplified, okay? Can't do anything with 2 ln 4 to the 3x. And technically, I don't need parentheses there, okay? But I can simplify the derivative of the inner function. 3 times 1 is 3, and x to the 0 is 1. Okay, so this becomes a 1. Okay, and why is that? Because x to the 0, anything to the 0 is 1. Okay, that's one of the rules of exponents. Okay, so this just becomes a 3. Okay, everybody all right with that? All right, if you wanted to, it would be possible to multiply these two together because they're both plain old numbers, and you could simplify it even further. 6 ln 4 to the 3. Okay, but please understand, everything from this equal sign to the right isn't calculus. This is all algebra. Okay, here's the calculus step. All right?
I have a question.
Sure.
I see how you got the outer, but how did you get the inner? I'm sorry.
Oh, no worries. The inner is the exponent 3x. Okay, so maybe it would help to differentiate 3x up here. All right, so it's 3x to the first, right? That's the thing that's up in the exponent.
Yeah.
Okay, so I'm going to bring down, this is just a coefficient of 3, so pull it away. Bring down your exponent.
Oh, okay.
And then subtract 1 from the exponent.
Okay, I get it.
That's 3 times x to the 0. 3 times 1. 3.
I just have to remember that there's a 1, an invertible 1.
Ask those questions, okay? Because all of this algebra is rolled up inside, okay? And what you need to do is you need to make sure you understand every step. It's perfectly okay to skip steps. You don't have to show every little blessed step like this if you can do them in your head. But if you can't, you want to write down the steps so you know how to get from here to here. Okay? So this is what we're doing. We're differentiating. Okay, so differentiate. Anybody other questions? Okay, so this thing I have with algebra underneath it, this here is your final result. That's your final answer. Okay, you could stop at this point. I think more would be okay with that, but you ought to be able to recognize, hey, here's a 3, here's a 2, everything's multiplied. 3 times 2 is 6. Okay, So again, you want to ask about the things that aren't making sense. Okay, why don't you try J? Okay, I'll try to leave as much of this up as I can. Okay, see if you can find J prime. I've done when you're finished. Find J prime right here. And again, I'll put it up here. The derivative of e, if y is e to the x, y prime is still e to the x. I gotta remind you how to differentiate the exponential. Okay, give it a shot. I put up some scaffolding if you're still trying this. The 5 coefficient, the outer function is e to something. The inner function is the linear 3x minus 1. Okay, let's wait another minute or so. Okay, everybody. I know some of you are still working on this, and that's fine. Not a problem. But let's all come together and work it together. And the only difference between this one and the previous one is we have a different base on the exponential part. Okay, the exponential base here is e. Okay, and you may or may not remember from last time, if I have the function y equals e to the x, the derivative of it is the same thing, e to the x. You might say, well, before it was ln of the base times the same thing. And it's like, well, yes, but that's because ln of e is 1. You're asking, say ln of e, you're saying, what do I have to raise e to get e? And that's a 1. Okay, so you can use the same pattern for all exponential functions. Okay, just remember ln of e is 1. So these with e's tend to look a lot simpler. You tend to not have the ln floating around in the derivative. Okay, so let's actually take the derivative of this, j prime of x. The first thing I'm going to do is pull through that coefficient. That coefficient is just comes right through. And then I'm going to differentiate the exponential, which is the base e exponential. That's just going to give me the same thing, just like this, right? If y is e to the x, then y prime is e to the x. So this is going to give me the same exponential. There's no ln, because ln of e is 1. This is the outer. Okay? And then I want to take the derivative of the inner, which is the exponent, the linear function up there. Okay, let's take a look at that. 3x to the first minus 1. And if I want to differentiate this, I bring down, 3 is a coefficient, bring down the 1, subtract 1 from the exponent. And again, the negative 1's a constant, so that doesn't give me anything. Okay, I could even say minus 0 if you want. Minus or plus 0 is not going to affect anything. Okay, again, constants by themselves give you a 0 when you differentiate them because they don't change. This becomes 3 times x to the 0, 3 times 1. This is very similar to what we did in the last problem. Okay. And again, you might recognize that these two are just numbers that can be multiplied together. Right, and there would be your final answer. Okay, questions on that one? Anybody have questions on that one? Okay. All right. Let me show you this example. I know it says you try, but let me work through this one myself with you. Okay, here I have a quadratic inside an exponential. Okay, and the 4 is a coefficient. Okay, so the 4 is just a coefficient. So if I want to take the derivative of k, I'm going to pull through that coefficient, and I'm going to differentiate the base e exponential, which is the same thing. Okay? No ln involved. But because I need to use the chain rule, because that quadratic is stuffed up there in that exponential exponent, I need to differentiate x squared. All right, and that's going to be bring down the 2, drop the exponent by 1. Okay, so here's the outer. Here's the inner. Okay, now it is possible, again, because of the way algebra works, it's an algebra thing. I can multiply 4 times 2x, and that will give me 8x e to the x. Okay, but that's an algebra step. You are done with calculus when you finish this first step. Okay, questions? Anybody? Questions? All right. Everybody getting the hang of outer, inner? Okay, and the trick when you differentiate outer is don't mess with the inner. Okay? Not until you're differentiating it. And if you have to actually write what I've written here, outer, inner, to keep things straight in your mind, do so. Okay, do so. Okay, the last type of functions we're going to look at are log functions. And again, let me see what I have down here. Here's the log that I'm going to show you. Okay. All right, I think we're going to just pick up the pace a little. So I'm going to ask you, rather than have you actually work examples, to please, look at what I'm doing and ask questions if you have them. Okay, because I don't want to run over time. Okay. So again, let's look at how we differentiate logs. Let's say I have y equals log base n of x, then y prime equals one over ln of the base times the argument. Okay, so essentially if I have log base, maybe I should make this an a because there's too many n's floating around. Okay, so I'll make my base a. All right, so there's the pattern, okay, for basically finding the derivative of a log. Okay, so it's 1 over. Again, the 1 over comes from the fact that logs and exponents are inverses of each other. Okay, so it's 1 over ln of the base times the argument. Remember here, this is called the argument to log. Okay, so there's the pattern that we're using. Okay, now if I look at my function L, okay, this is a quadratic inside log. Log base 2. Okay, everybody see that? Because again, the first thing that would get x would be the argument to the log. Okay, and that's a quadratic function. So I'm going to try to differentiate L prime of x. Okay, so I want to do the outer function, which is my log function. Okay, so that is going to be 1 over ln of the base, which is 2, times the argument. Okay, so that's the derivative of the outer function, the log function. And that gets multiplied by the derivative of the inner function, which is my quadratic. Okay, so if I have x squared minus 4 and I want to differentiate, okay, I'm going to bring down the 2, drop the exponent by 1, and the constant gives me a 0 in my derivative. So this is 2x. Now, what's important to realize is the way I wrote this might seem a little confusing. Let me write it in a way that isn't confusing. Okay, so where's the 2x? Numerator or denominator? Where's the 2x?
Numerator.
Yeah. Okay. So let's take a look. Okay, there's your final result. Okay, you can leave it like this, but again, I want to make sure everybody understands this is 2x over 1. Okay, so the 2x winds up in the numerator. okay, and your arguments down here. Lots of times if you've got like a 5x in here, you'll wind up with a 5 on top and a 5x on the bottom, and they'll cancel, okay, if you want to simplify further. But this one, I can't simplify any further, so that's my result. Okay, so let me stop. Since this is the first log one we're doing, let me ask if you've got questions. Okay, so here's the log pattern that I'm using. The patterns are from yesterday, okay, and I'm just using them. Okay, the only difference with base E is you wouldn't have this ln, because ln of E is a 1. So all you get is the argument downstairs. Okay. Let me do one with base E. Okay. Again, how do I know it's base E? Remember that ln means base E. Remember, ln means a base E log. Okay. So this 6 is a coefficient. Okay, and this is a composition of a linear inside base E log. Okay, everybody all right with that? Okay, so if I want to find m prime of x, I'm going to first pull through the coefficient. And then I'm going to take the derivative of the outer function, which is the log. All right, so that's going to be 1 over, again, I would say ln of E down here, but ln of E is just a 1. So I'm only going to wind up with this. Okay, it's also important to realize this 6 is 6 over 1. So that 6 is also in the numerator. Okay? So far, so good. All right, and now we need to differentiate the inner function, which is the linear function. All right, 5x minus 2. All right, so that's 5x to the first. Bring down the 1. Drop the exponent by 1. Constant doesn't give me anything. This is 5 times x to the 0. And that's 5 times 1, which is 5. Okay, so it's important, again, if you can do these steps in your head, that's great. But if not, write them out. All right, so this just gives me a 5, and it's 5 over 1. So what's in the numerator here? What's in the numerator of this derivative? Anybody? I know my denominator is 5x minus 2 times 1 times 1, so 5x minus 2. What goes upstairs? 30. Okay? This is 6 over 1 times this fraction times 5 over 1. I can multiply in any order, so the 6 times 5 shows up here. Okay? This little bit is not calculus, it's algebra. Okay? Okay with that one? With the log examples. Anybody have questions about the log examples? Okay, so you can see what I'm doing in these examples that we've done so far today is I'm using multiple patterns. I'm either using the product, the power rule, or I'm using the pattern for exponentials, the pattern for logs, and the chain rule pattern. Okay, so you've got to be comfortable with using multiple patterns. Okay, comfortable with using multiple patterns in the same problem. Okay, that's why it's absolutely crucial to stop and look at what you've got before you actually try to do calculus on it. Okay, spend a little bit of time actually saying, okay, this is a composition, this one's the inner, this one's the outer, or wait, this is a product, okay, and these are the two functions, right? It really is worthwhile slowing it down. I'm actually telling you, do math slower, okay, and think about what you've got, okay? I'm going to skip the next couple of U-tries, that U-try, and I'm going to move on to this because I want to make sure you see it before you actually attack your homework, okay? The chain rule can be combined with product and quotient rules, okay? So let's take a look at P of X. Okay, so look at P of X. What is its structure? Okay, look at P of X. What's its structure? Is it a product, a quotient, a composition? Okay. Anything else? I see the product. Yes, I do. Okay, so the topmost structure is a product of an exponential. Okay, so I've got this first bit here. What's this bit? Exponential and what? What's the second factor? Yes, it's a composition. Okay, and a composition of a linear inside a polynomial. Okay, does everybody see the pink thing that I've highlighted is a composition? So how do we attack this? Okay, we have to use our product rule, but when we take the derivatives of each of the factors, we're going to need to use the chain rule on one of them. Okay, does that make sense to people? Okay, so start with a product rule. Okay, so P prime of X, let's call this F, and let's call that G. Okay, there's the product rule. Okay, so then I have F equals e to the x, F prime equals, well, e to the x. Okay, it's the only function that's its own derivative. Okay, G equals 2x minus 1 to the fifth. G prime equals, I have to do the inner-outer business again. Okay, my polynomial is my outer function. So I need to differentiate that first. Bring down the 5. Drop the exponent by 1. And don't mess with what's inside. Okay, then I have the inner, which is 2x minus 1. Okay, and the derivative of 2x minus 1, that's 2x to the first minus 1. I want to differentiate that. 2 times 1, drop the exponent by 1. The constant gives me nothing. 2 times x to the 0, 2 times 1, 2. Okay, I hope you're getting to the point where you can look at an x and realize its derivative is 1. You can look at a 2x, realize its derivative is 2. You could look at negative 5x and realize its derivative is negative 5. Okay, that will speed things up. Okay, but if you have to go through the steps to get there, feel free to do that. Okay, so here I have 2. Okay, and again, I might want to simplify this because I'm going to put it somewhere else. Okay, so I just multiplied the 5 and the 2 to get the 10. Okay, now I'm going to just use my pattern for the product rule, which says take the derivative of f, that's e to the x, multiply it by g, okay, plus take f and multiply that by g prime. Okay? Everybody all right with that? Okay, just plop it right in the pattern. So I'm using this pattern up here, and I'm just saying here's f prime, here's g, here's f, here's g prime. If you want to walk away from it at this point, that's perfectly okay. Some people would continue to simplify saying, hey, I can take out an e to the x from both of these terms, and I can also take out 4 of the quantity in parentheses. So this can be simplified further. Okay? But I'm going to skip the algebra. Okay? This is the calculus step. Anybody questions on this? Questions on the chain rule inside the product rule? Okay, and it's the chain rule inside the product rule. That's what I mean when I say look at it really carefully and make sure you see what's there. Okay, I'm gonna wait another minute or so to see if more people respond, okay? Please just give me a shout out. How you doing? Anybody questions? Okay, please give me a yes or no. And again, I said it at the beginning of class, but I know we had some folks join us a little late. If you decide once you start doing the homework for this section that things start swimming and you get lost, feel free to reach out. Okay, you can do a couple of things. If you just want to do like asynchronous email, you can click that message instructor link at the bottom of the problem and it'll send me an email. It'd be helpful if you told me where you got stuck, but if not, I'll work the problem out for you. If you want to have a face-to-face conversation, we share screens and things like that, just let me know and we'll find a mutually convenient time to set up a one-on-one WebEx meeting. Okay? So please, please don't feel like, you're on your own here. Okay? I'm here if you have questions. But reach out to me. Please let me know. Okay? All right. I just want to show one more thing. I'm skipping the U-tries, but I will fill them out basically, with my own work when I upload this. Okay? Take a look at example 5. What's the structure of example 5? What's the structure of example 5? What are you seeing? Okay, for sure there's a composition in it, for sure. What's the high-level structure? Absolutely, it's got a composition in it. But what about the e to the x upstairs? That's not a composition. Is it a product? Is it a product if it's a fraction? There's a divide sign between the numerator and denominator, right? A fraction bar means divide. So what do you think? Is it a product? Could you write it as a product? Sure. Okay. You can think of this as a quotient of an exponential and a linear inside a polynomial. Degree. Okay, does everybody see it? Okay, you can look at it as a quotient, but I think why some of you are saying it's a product, okay, you can also see it as a product. If you do a little bit of rewriting, e to the x times 2x minus 1 minus 3. Okay? And basically you've got, it's a product of an exponential and a linear inside a rational. Okay? Now, had I put the composition on the top, you'd have to use the quotient rule. Okay? You'd probably have to use the quotient rule. Right? But here, you've got two ways to go. Do I care which way you use? No. Take the easy way. Okay? What you have to understand about higher level math is there's usually multiple ways to get the right answer. As long as they're mathematically justifiable, they're perfectly okay. I'm not going to tell you you have to use the quotient rule here if you can rewrite it as a product. As a matter of fact, it's probably easier to do it as a product. Okay? But again, if you want to use the quotient rule, here's the rule you're going to use. Let's call this F. Let's call this G. Okay, we have G times F prime of X. Again, I learned this in a different order from you. So I'm trying to keep it like what your book has. F prime times G minus F times G prime all over G squared. This is the way your notes say it. Okay? So then what you need to do is you need to find F prime, G, and G prime, which again requires you to handle the composition. Okay, so outer and inner. Okay, so bring down the 3, drop the exponent by 1. Don't mess with what's in there. Okay, and then take the derivative of the inner. I'm going to cut to the chase and just say that's 2. Okay, because again, the minus 1 doesn't give me anything, and the derivative of 2x is 2. Multiply these two together. Okay, I've just multiplied the 3 and the 2 to get a 6. Okay, and then you just plug it into this formula over here. Okay, so just plug in the bits. So that's e to the x times 2x minus 1 cubed minus e to the x times 6. And then the whole thing over g squared. Okay. Can this be simplified? Oh, you betcha. Okay. There's a couple of things you could do here. In the numerator, you could factor out an e to the x. You could also factor out 2 copies of 2x minus 1 because they'll go here and they'll leave 1 behind here. And then if you're raising a power to a power, you could change this into a 6. Okay. You can also do it with the product rule, okay, where this is f and this is g. Okay, but again, you would use this way of doing it. Okay, and I would guarantee you this comes out simpler. The only thing here is you might say, well, wait a minute, this gave me a fraction. Yeah, and this one's going to give you negative exponents, which technically will be the same thing. So the results may look different, but they'll be equivalent. Okay, the results may look different, but they'll be equivalent. Okay, everybody good with that? So again, see it as whatever looks easier. Okay, if you look at this and say, hey, it's a fraction, and there are x's in the top and bottom, I need to use the quotient rule, go for it. You'll get this as the answer. Okay, so questions, anybody? I know that most students find the chain rule a little difficult to wrap their mind around, especially when you mix it up with other rules. Okay, but I wanted to show you these last two if for no other reason that you can recognize them as chain rules inside of product and quotient. Okay, I'm going to come back to the meeting and ask again if we've got any questions on anything. Okay, any questions on anything? How are we doing? No? Okay. If anybody wants to stick around to ask a question, that's fine. But I have nothing else for today. That certainly was plenty. What I would suggest is email me or reach out to me if you're struggling with the homework assignments. Okay? Don't struggle by yourself. Okay, at least not past a reasonable amount. Okay, otherwise I'll see you Tuesday.
Bye.
Bye.
Thank you. Have a good day.